Okay. I actually had to scrap this. I'm starting over on one. I recorded for 15 minutes, almost 14 minutes, and it was a piece of crap. And so I'm doing it again. But we're going to talk about capacitors. Two places where you have. Oh, so anyway, stores charge. I got to be able to store this thing. I got to be able to charge this thing up so that it stores charge, so that I can call. But every time I use it, it takes a little charge out. Then I got to plug it back in. Capacitors in it. Here is a real industrial capacitor that my friend and colleague down the hall, Tony Caruso, gave me, and to show that most capacitors are not parallel plates. As a matter of fact, there's thousands and thousands of little spirals along in here. Thousands of them, millions and millions of little spirals in there that are positive and negative charges wrapped around each other. Okay, so it stores a heck of a lot of charge. Stores a heck of a lot of charge. Okay, that's a real capacitor. Depends on the capacitance, depends on the geometry, the materials used. Parallel, really. And in the last movie that I erased, I explained it horribly. I mean, horribly. All right, so this one will be better. Okay, so let's just go to the slides. Let's back up. Okay, here it is. Q is equal to CV. There's your first equation for Q is equal to CV, and it's in coulombs per volt. All right. So in other words, the amount of charge, and we just pick one of the plates because positive charge, the amount of charge over here is going to be the same as the charge over here. One's is positive, one's is negative. And that causes that potential difference, which pushes charge around. And we've got an electric field that's wide open in there that's coming through there, okay? So Q is going to stay the same. Q is going to stay the same. All right, so now, dielectric constant. What we do is we actually put something that is non-conductive, slide that in there, and here's what happens. The positive charge surface on the dielectric lines up with the negative charge surface over here. And the negative charge surface lines up with the positive charge surface over here. So look what happens. I've got a much smaller electric field. I've got the same electric field, but look, it's going less distance. So the voltage is dropping. So I'm getting less voltage. Some of it's going all the way through. Some of it's going all the way through, but some of it's just sticking right here, just going from here to here. So the voltage drops way down, but the charge stays the same. So if we want to keep something constant, look at here. Capacitors. Storage and energy. So if we want to keep something the same, so if we got Q is equal to CV, all right, and we put this dielectric constant in there, here's what happens. We get Q stays the same is equal to a bigger C. Since the Q stays the same, what has to happen to V, the voltage? It goes down. So we don't need to increase our capacitance. We just decrease the voltage required. And so to charge it up. So now I can charge up. All right. Cool. And when we put this dielectric constant, and that's what the dielectric constant does. All right. It is our new E divided by the old E, which this electric field is now smaller. Now look what happens. It's greater than 1. Water is a great dielectric constant. Pure water. But it's hard to work with. All right, it's kind of mushy. It doesn't want to stay in one spot. What is the shape of water? Anyway, so methyl alcohol is another good. Rubber, see, you got these ruby and mica and all that kind of stuff. It's measured in farads. Most of our measurements are going to be really small, like farads 10 to the negative 9, 10 to the negative 10. That one capacitor I showed you, 3,000 farads. Very low voltage, though. All right. The capacitance of a parallel plate conductor. Okay? All right. Okay, so the electric field, the electric field actually gets smaller in the, so therefore the electric field times the distance, so the electric field gets smaller. So that's why it was E naught over E. No, the electric field stays the same. When we put in a dielectric constant, the electric field gets, that still is not making sense to me. But this works out. Oh, I've screwed this up again because I'm not looking at this correctly. Remember, here we go. I'm sorry. This is bad. This is bad. All right, so E, remember E, electric field E is equal to, according to the electric flux, remember the electric flux thing? Equals amount of charge over echo naught. Okay, so in this case, we're just looking at a parallel plate. So we're saying that E is equal to Q over A times echo naught. Okay, and then what they're doing here is they're taking that, that's what we got, and they're saying, all right, well, then that's E naught. They're saying that the new E is equal to E naught divided by K, which equals the voltage divided by the distance, which is variable in here. Okay, so here's what we did. We go to E, so then they're saying E is equal to E naught over K, which is equal to the voltage over the distance. Okay, so Q is equal to K E naught A over D once we plug this E naught in here. All right. Just trust me on the algebra. No, I'm going to do it. Damn it. I'm going to do it. E is equal to E naught over K. Okay, because K is equal to E naught, the bigger electric field, over the new smaller electric field. Forgot, we're reducing the electric field. Okay, so if I put this E naught in here, if I put Q over A times echo naught over K, that's what the new E is equal to, which is equal to V times D. Okay. So I want to solve for Q. So I get Q, no, V over D, because the electric field is equal to V over D. I am so sorry for this. And so this is why I never do derivations, because I just want to get to the formula. All right, but anyway, so I'm going to solve for Q here. So I got Q over A echo naught divided by K is equal to V over D. Or in this case, by this time, this lecture is VD. Anyway, no, kidding. Stop. Stop. All right. How do I get rid of my V? Oh, it's still there. Oh, this becomes C. I see, because it's equal to C. Q is equal to C times V. Cool beans. So I get Q over AEK is equal to, oh, sorry. You should never do this shit when you're tired. All right, is equal to D. Dun, dun, dun. And so Q is equal to A E naught K over D. times V. So this is equal to my capacitance. So that's your big formula. C is equal to, we usually write it this way, the dielectric constant times A echo naught over the distance between the plates. All right? And then we also know this. Here's the other thing. We know that Q is equal to CV, and we also know that the electric potential energy is equal to Q times V, except for parallel plates because they're time dependent. They've got to charge up. Because they got to charge up, they start from 0 and go to their maximum. So you got the average charge, which would be 0 times the maximum divided by 2. Okay, so the EP for a capacitor, the energy in a capacitor is equal to 1/2 QV. All right, and if V is equal to Q over C, okay, then we've got the EPE is equal to 1/2 Q times Q over C, which equals Q squared over 2C. That's 1. And if we also know that Q is equal to C times V, then we know that the electric potential energy, so this is one formula for the energy, then the other one is 1/2 CV, because I'm taking this Q, plugging it in there, times V, which is 1/2 CV squared. There we go. That one was still a little choppy, too much derivation, too late in the day, but that's